So now we're going to talk about integrating ECG and triaxial motion data for heart rate detection and early heart disease detection as well. So we're going to be using AI image recognition and machine learning. Now let's jump to our first section of why this project is significant. Alright, so cardiovascular diseases is a leading problem that causes mortality around the globe. So this is normally because hospitals can only track about a minute of ECG data while you go to the hospital, and then once you come back out, they stop detecting. So our solution is to have a 24-hour wearable device that constantly tracks your electrocardiogram signal as well as a triaxial accelerometer data. And together, this will create a great foundation for AI image recognition or machine learning. So next, let's talk about why the prolonged data is better than hospitals right now. So right now, we can, the project can capture data for 24 hours, and this means we can capture the that means we can capture the cardiac events while it's happening. Meanwhile, in hospitals, people normally go there after a event such as arrhythmias or heart palpitations. So then, doctors can only see what's going on after the event. Here, with our wearable device, we'll be able to see the event happening in real time. Alright, next. Okay, so the project right now is to use 24-hour ECG data with a motion capture triaxial accelerometer, and this is a research realm that hasn't really been touched yet. Sure, there has been stuff about sleep with motion and ECG or certain diseases, but not everything at once. So this is an unexplored field. Okay, so AI machine learning may be great at finding patterns and trying to detect what anomalies occur, but of course we have to trust humans, right? So the data can be visualized for humans as well. Doctors can then check the raw data, and then we can see if their results correspond well with the conclusions drawn by AI, and we can either uh, recalibrate it or it can stay the same because it's doing good. Alright. In conclusion, we are switching to a proactive state instead of reactive. We can allow hospitals and doctors to detect these signs earlier. So instead of trying to treat it while it's at a really worse state, we can detect it early on and create good treatments early on. This way, it'll lessen the burden on our healthcare and save lots of money. Okay, now we're going to talk about how all of this is implemented. So first, let's understand the theory of how we get our ECG data. So first, we have a heart. Everything is based on this heart. So the heart, how this works is it starts with the right atrium. The right atrium convulses to draw blood from the superior vena cava and the inferior vena cava, and the blood from here travels to the right ventricle. And at the same time, the left atrium draws fresh blood from the pulmonary veins, which goes into the left ventricle. Ventricle. Yeah. So these veins are full of oxygen because we breathe them in, and these are blood returning back to the heart, which is now which doesn't have oxygen since the oxygen has been supplied to the cells in our bodies. So notably, the blood coming back that has no oxygen in it is blue, and the ones full of oxygen is red. So the contractions and convulsions are what cause the electrocardiogram data that we can detect. And these are like this. This is a normal wave. So there's the P, Q, R, S, J, and T. So the PR is from the start of the P to the start of the R. PR. And for what we do, normally we try to detect the R peak, since this peak is the highest peak with the highest slope, and it is the most obvious. So to find heart rate, we can find the interval from the R to the R. So this is 1 beat or 2 beats, right? Boom, boom. And then, yeah, that's our current algorithm, is to find the intervals between the RR peaks, and we can find heart rate using an algorithm based off that. Alright, so this is the QT. This is basically explaining what each segments do. So all of these segments can be used to find different diseases and arrhythmias, and AI is really good at image detection, which can really help the process. A doctor is not going to sit there for 24 hours and just look at the data pass, and this data, being able to identify where each of these nodes are, is really important. Alright, next we're going to talk about the hardware setup. So we have a image here at the bottom, and so by the way, this is a prototype, so it will be able to be smaller and lighter later on. So I have the hardware with me right now, right here. So this basically explains what this does, and I'll explain it here, right? So at the really bottom here, this is the Arduino Uno board, and then on top of it is the data logging shield. So there's an SD card. There's an SD card that stores all of the data that we get. And then from this board, there's a few sensors that gets data for us. So here, this is the ADXL345. It is the triaxial accelerometer data that we can get motion data from. This is a key component. And then here we have the electrocardiogram data collector. We can, sorry. So here we can plug in the lead wires leading to the electrodes over here. And then here we have a button that can be pressed down. This button can be used by the patient to indicate that they feel some distress at the moment, and they can press it down. This will annotate sections of our data so that doctors can focus mainly on the parts where the data was pressed. And then back here, this is the power supply module. As you can see, there's a power jack, and you can use USB if you want. And this module is what gives this whole thing power, so that when it's carried by a person, we can simply put a few batteries here. Over here, we're going to use 18650s, which are really good batteries, and they last a really long time. And yeah, that's the hardware setup. Alright. Yeah, it doesn't seem like I lost any of the sensors. I forgot to mention none of them. Okay, next we're going to talk about the data format that we log onto the SD card. So here we have, this is the basic data structure for one entry. So it starts with the timestamp. This timestamp starts from 0 and counts up in milliseconds. And then here, this is the ECG data. So this is, and then we can visualize it like this. So the ECG data looks like this. This is the raw data without any processes. And then the next three for the data structure are the x-axis, y-axis, and z-axis for the triaxial data monitoring. So as we can see, 6, 16, and negative 287. So these show how the person is moving around in the real world, and it will be reflected in this model as it can shift around as well to mirror the data. And then the last one is a Boolean. This shows whether the button is pressed or not. If it isn't pressed, it's at 0. And if it is pressed, it's at 1. So this will tell us when the user has pressed down the button and is in distress. And when the button is pressed down, this will become red, and there will be a warning sound that will be played for the doctor. Alright, and then moving on, we have the code writing. Okay, so the Arduino microcontroller can synchronize the data that comes from all the different places. So from the ADXL345, the triaxial motion sensor, the ECG data, and the button. The Arduino microcontroller mashes it all together into one data structure that we talked about before, and puts a time at the start, and then logs it onto the SD card. And then we have to verify that the data that we capture is correct, right? So the most important part is to visualize the data. We can see the data, so we'll know if this is correct or not. As we can see up here, we can see that this data we captured is pretty good in quality. And next steps, we can use AI and stuff. Okay. Right, so we paired up the ECG data, the motion data, as well as the button press and a time. Okay, next we're going to talk about the algorithm for getting the heartbeat or the heart rate. So as I talked about before, the R peak is the highest peak, the most obvious peak with the steepest slope, and our algorithm can pick up on where the R peak is compared to the other ones. And then we find multiple different R peaks to find the RR intervals, and through this we can calculate the heart rate. Next, we're going to look at the product outlook, so what we plan on doing with this project next. So on the client side, we're going to make it more portable. So the prototype was quite big. We want to scale it down to about this size, 3 by 10 centimeters. And if it allows, we can maybe saw some off and make it even shorter. So that's the first plan. We're going to make it more compact. We will be using a sandwich structure. That means we will have stuff at the top and at the bottom. So that way it's more space efficient. And we will choose to have a smaller central processing unit. So instead of the Uno board, we will instead choose the Nano board. This is smaller, and we don't really need that much computational power, since all we're doing is recording the data into our SD card. And then next, we plan, since someone is going to be bringing it around, lugging it around the whole time, we plan on making this less than 90 grams. So, and that includes the batteries. So in total, it would be quite light, and it wouldn't be a burden for the person to carry around. And finally, since there are no servos or motors on this whole project, this will be quite energy efficient, and we plan on only using one battery, 18650, and I think it will be able to last for 72 hours, but for conservative sake, we'll say this can continuously operate for 24 hours. And we will also add a module that allows the battery to charge more easily. So after, let's say, 24 hours or 72 hours, the user can plug it into the charging cable and let it charge. It will be really easy to recharge the battery on this. Alright, next we're going to talk about lab side improvements. So in order to actually have the AI model or a large language model running and actually analyzing our data to find the heart diseases like arrhythmias, we will need a good GPU that can train the AI model. So we are thinking of the NVIDIA GeForce RTX 5090. So this is one of the most popular GPUs currently available for training AI models. This will allow our training process to be efficient and quick, and this would make the models a lot more optimized. However, this GPU is quite expensive, so our plans for funding include grants, crowdfunding, and partnerships with tech incubators. These are some ways that we will start gathering the funds to buy this GPU. And all of these plans will start fall of 2025. Here's a picture of the PCB with some nanoboards and some other stuff attached right next to our prototype. As we can see, this is quite a bit shorter and a little more narrow. And this will only use one battery cell instead of 3 like right now. Alright, now we're going to talk about the appendix. So first, this is our processing code that we use to detect the R peak in our ECG data. So this is the void detect R wave function. First, we set a dynamic threshold. This threshold is used to determine whether the potential R peak is an actual R peak. If the ECG value is bigger than the dynamic threshold, that means it's a potential R peak. And then to validate if it actually is a R peak, we see if it is within the time frame of another one. So as long as the time frame isn't isn't bigger than, like, I believe 170 something beats per minute, then it'll assume this is a valid R peak. And then after we find a new R peak, we need to add it to the timestamp and the R interval, and then we keep a size of 10 R intervals to keep our database. It's kind of like a small database of the last 10, and we can use this to calculate beats per minute using the average of every time in the database divided 60k divided by this. 60k is a minute, and since currently our ECG value is in milliseconds, so then this would turn into minutes, and then we can display this last peak time and then baseline threshold. We can update our baseline threshold, which will then update this and the dynamic threshold next time the detect R wave function is called again. Alright, next we're going to talk about the Arduino code. So this is the code that's burned into the Uno board. So first we start with a while true loop. So this is an infinite loop that ensures the program runs continuously and processes the data while it's running. So first we look at the ECG file. So first, the file is called ECG data.txt. So this is a text data, and it contains the timestamped ECG readings. So first we check if the file needs to be restarted, and we see if the ECG file is available. ECG file is available, and if it isn't, then we close this and we stop the true loop from running. If we can read it, then we close the file and we continue on. But if we can't read it, then we stop the loop from running. And here we turn the LED on. The green LED basically means that the code is running properly right now. And then here we can parse the ECG data together into the data structure that we talked about: timestamp data, ECG, XYZ, and then button. So we do the timestamp, and then we find the accelerometer data, so X, Y, and Z, and then we read the data from the ADXL345, and then here we see what the button is doing, if it's at 0 or 1, and then we write that in as well. So we combine all of our data, so the timestamp, our ECG value, X, Y, Z for the triaxial accelerometer, and then our button state. And then we put this onto one line into our ECG data text, and then we make sure the data is written immediately. So we do a flush, and then we turn the green LED off for a little to show that it's processing data, and then wait for a bit, and then we do a complete loop back to the true statement, and then we check again, and so on. Alright, so now that we plugged in the USB cable into our Uno board, the data from the SD card can be read directly into our computer. As you can see, the green light is on. That means the data is being read successfully. Here we have our processing IDE open, right here. And then we can run the code here by pressing run. And then the window will pop up. And here we can see the ECG data is being uploaded from the start. And then here's the timestamp, here's the whole data. The timestamp is the first one, and then this is the ECG data. It's going up and down, and then this is the X, Y, and Z axes for the ADXL345, and then this is directly linked up into this model. So if we turn our prototype around, we can see that this model shifts with our sensory input, and then we can tilt it backwards and forwards. Alright, and then the last one is the button. So if we press it, which is this button right here, the sound will come on. And then we can see this button will also turn red, as well as this light. Let's see. And then when this is pressed, that means this will be 1 instead of 0. Alright, that's about it. Thank you.